Well, hello everyone. Welcome to the, actually it's the second webinar on the dimensional management topic, and this time the main topic is how to define a functional datum reference frame. It's the same format, that's and the same people presenting. So it's Cédric Chénet, which is for those who might not know him, a graduate into aerospace engineering techniques from the École nationale d'aérotechnique in Canada, and he has more than 8 years in dimensional management application and GD&T concepts, and he's worked basically in the aerospace and transportation industry. And myself, I'm a mechanical engineer myself, and I've been working with Creaform for over 12 years now, so involved into metrology and developing products along these years. And as I said, this is the second webinar on the the dimensional management topic, and actually we'll go through the agenda. So the format is quite simple. I'll take maybe 5 minutes to introduce to what Creaform engineering, Creaform in itself, and Amatec, and then we're gonna get into like the review or overview of the dimensional management process, the different steps, and how we at Creaform we deal with dimensional management. And then we're going to get more into the core presentation where Cedric is going to present how to choose the datum reference frame and depending on the type of parts you have in assembly. So more technical, more into technical side of it, and then we'll conclude, and then we're gonna have a question period at the end. So you might ask questions during the presentation, but actually we're gonna keep your question, and after like 30-minute presentation, we'll go over those questions and try to answer most of them, depending on the volume we receive. So don't hesitate to ask questions during the presentation, and you can refer to slide numbers so that it's easier for us at the end to get back to the specific questions. And then there's also a survey at the very end of the meeting. When you're going to close the window, you can have a survey. This is really important for us. We make the presentations and the next webinars on the topics that the people want to see, want to hear about. So if you guys have very specific things that you would like us to present, make sure you let us know into that survey so we improve our next meeting and make sure it's very dedicated or specific to what the people watching the webinar wants to see in the future. So we appreciate your feedback. So basically, so for those who might not know, I'll go very fast. So because we want to get to the topic right away. But what is Creaform engineering? But basically, it's a consulting firm which is part of Creaform, and Creaform is part of Amatec, and we're about 185 technical people, expert working in different fields, but also almost all into mechanical engineering. But there's also some other stuff we touch to. We have different offices in Quebec, Turin, Quebec province in Canada, but we also have an office in Irvine, California, and then Creaform has an office across the board, across the world. And as you can see now on your screen, there's all the technology that Creaform develops. It's part of what we call a techno group. So and all of those equipment are metrology grade technologies. So it's optical measurement devices. So there's a huge link with the dimensional management services we offer at Creaform Engineering. And Creaform Engineering is a division in itself. It's a standalone. So when we take the whole company, it's about 600 employees. So I know, and the company was founded in 2002, so it has about 18 years old. And Amatec acquired Creaform 7 years ago, almost now. And we're part of a subgroup in Amatec, which is ultra precision technology. So we have sister companies that develop also technologies that relates to the technology you see now being developed at Creaform. So that's it for the corporate overview. If we get to the next slide, well, it's actually about Amatec, but Amatec is a huge or large public U.S. corporation with 15,000 employees and location across the world and over $5 billion in revenue. So it's a sound company developing like really a lot of different technologies, and then there's different subgroups where they're more into advanced metrology and measurement application and devices, which we are in. So that's it for a more corporate portion of it. And then if we get back to what is Creaform engineering, Well, it's a product development offer that we have, and we accompany our different customer in developing their product and bringing them to the market. So by also accompanying them to manufacturing a portion of the whole process. So we start from the ideas, so industrial design and everything needed for advanced engineering, just making really putting ideas to life, so sketches and everything, and we get to the point where we can develop tooling and everything, automation projects for manufacturing portion of it, and everything in between. We cover a lot of that, so mechanical engineering, automation, electrical engineering, project management, prototyping, a lot of simulation. Also, we have 15 people in simulation only, so structural and CFD. But then what we want to see today is the dimensional management portion. And that is our friend Cedric today that will present the topic, and he's going to show you through a product the different ways we can and the proper way to select datum when you're developing a product. So I'll let Cedric handle the rest of the presentation.
Thank you, Martin. So hello, everyone. Welcome to our second webinar on dimensional management. For those that have missed the first one, it is available in the news section of the Creaform engineering website. So the goal of the first webinar was to have a quick overview of the 6 steps of dimensional management. And in a survey at the end of the webinar, we asked you which subject you would like us to speak in greater detail. So by popular request, today we will talk about GD&T and more specifically, datum definition, like Martin said. So we'll do this in 3 steps. So first, we will start with a little bit of theory. And then we will look at the good practice when that we should observe when defining datum. And then we will go through a few concrete examples and actually define datums on different types of parts. So as a start, we just want to repeat the goal of GD&T is to communicate the acceptable geometry of a part. So to do this, if we want to simplify a lot, we only need really 2 things. So we need a reference system and an acceptable tolerance zone inside which our geometry must be located. So today we will focus on the first point, the definition of the reference system. So before going further, even if most of you must be familiar with the concepts of datum, I think it's worth it to start from the base and ask the question, why defining datums in the first place? So why a good old 2D linear dimension drawing like the one we see on the left of the slide here couldn't do the job? So if we look at the right, we have a definition with a basic dimension of 60 and a profile tolerance of 10. So we have a tolerance zone of 10 that is centered on the nominal, so 5 on each side. So in short, 60 plus or minus 5, which at first seems to be exactly the same thing as what we see on the left. So we start to understand a little bit the difference between the two when we want to measure a real part. So on a real part, a bit like you see on the screen, there will always be some dimensional variation. So if we want to measure the 60 plus or minus 5 like it is requested, first question that we might ask is, where should we take the measurement? So is it at the largest portion of the part? Is it at the smallest portion? And also, how should we orient our measurement? So one could bring a good idea and say, we could use a straight edge or put the part on the flat inspection surface in order to be able to measure perpendicularly from that surface, and then try to find where is the worst deviation on that part. But the problem with that is someone else might do exactly the same thing, but use the other surface as a starting point. So in that case, the two would be right in theory, but the two measurements won't be equal, and only one of them would be able to tell us if the part will fit or not. So the reason why we have this ambiguity is because we are missing one information. So in order to measure a part correctly, we must know how it works. So if I take this assembly as an example and I say, this is the way the blue part should be installed in the next assembly. So everything fits together nicely. We don't have any clash between the parts. But if we change the way the part must be used and we say, no, that's not the way, the part must be used this way, we now have a clash right here. So we are seeing this difference even if we are still using the same two surface of the part and the counterpart. So in both scenarios, we would have had the same 2D requirement on a 2D drawing, but only, so we were missing one information. So we had more than one way to control the same requirement, but only one was able to tell us if it was fitting or not. So this was just a small example to remind the concept of datum, and I think it's also a good way to introduce the official definition of a datum, which is a theoretically exact point, axis, line, plane, or combination thereof, derived from a true geometric counterpart. So on the picture, just below the definition, the true datum here is really this one. So the datum is really the origin from which we will measure the part. So that's the reason we want it to be a perfect geometry. So we have now arrived at the part where we talked about the good practice of datum definition. So there are a lot of them, but we have identified 4 characteristics that we judge to be important. So we will present them with very simplified example of datum definition that do not follow these example. So the first will be functionality. So what we mean by that is that ideally a datum should be defined on a functional surface of a part. And it's even better if we can select a surface that is locating the part in the next assembly. So if we have a part like this one in gray that is to be installed on the yellow part like this, it won't be very functional to define datum on the surface. So sometimes it can happen that we don't have the choice and we have to define datum on non-functional surface, but if it's possible, we will try to avoid that. So the second one will be repeatability. So in the example here, if we have a part like this and we decide to define the datum at the end of the small arm like this on that very small surface, it won't be very stable. So repeatability won't be there. So in the example here, we are showing a lack of repeatability caused by a datum on a surface that was too small, but we could also have the same kind of problem by choosing a large surface, but with a very poor surface quality, a bad flatness. The next one is ease of use. So obviously, if we are not able to use the datum during the manufacturing or inspection of the part, we won't be much better off. So in case like this example right here, if we have some kind of cylinder with a welded cover like this, and we decide to choose a datum on the inner diameter that we don't have that we can't access, well, that won't be a really good choice of datum. So this is really an extreme example, but when we talk about ease of use, we also talk about any kind of datum that will require the complex setup to properly hold the part. So sometimes we don't have the choice to do it, but if it's possible, we will also try to avoid this. The last one is clarity. So what we need is for anyone who read the drawing to understand exactly the same thing. So if we have some kind of rail like this on which we have a center line defined, it won't be a really good idea to define a datum on that. So just by reading the drawing, we have absolutely no indication about which feature does that center line refer to. So are we talking about the base? Are we talking about the upper portion? Or are we talking about the center of the slot? Just by reading the drawing, there's no way to tell. So that's about it for the main good practice we will try to observe when defining datum during this webinar. So we will keep them in a small box like that, and we will bring it back to evaluate our choice when we will go through the example in the next slides. So for the case study, we will use the same example as in our first webinar, the ATV suspension. So this is a very good example for this webinar because we have a good mix of different kind of parts. We have machine parts, we have a casting, we have some weldment, and we have flexible plastic parts. So we will go through them one by one in the next slides, starting from the one at the bottom, and you will see that the complexity might go up as we evolve in the kind of part we are looking at. So the first one we will look at is really the simplest, so it's a machine part. So the first thing we will want to do when defining datum is to understand how the part is installed in the next assembly and in which order. So for that part, we will start by inserting it into the knuckle. So making contact with the diameter, that step will lock some of the degree of freedom of the part. So in that case, if we look at the small axis system on the lower left corner of the slide, we will look the translation along and the rotation around the X and Z axis. So in other words, once the part is constrained on its diameter, the only movement that it can make is translate along the Y axis and rotate around it. The second feature that will make contact on our part is the shoulder of the spindle. So this contact will log the translation along the y-axis. So once that is done, our part is completely located in its assembly. And in that case, you will see that the rotation around the y-axis is still free, but with a cylindrical part like this that don't have any distinctive feature around its diameter, it won't be necessary to lock it. So how does it translate in terms of datum on a drawing? So well, first we add the diameter that we can constitute our datum A. Then we will have the shoulder of the spindle that can constitute our datum B. A good thing to remember when defining datum like this is that it will often be a good idea to ensure that the datums have a good relation between themselves. So in the example here, we could define a perpendicularity control on our datum B like this, and that will ensure that it will always keep a good orientation with relation to datum A. So if we bring back our evaluation grid from the beginning, for this one, it really haven't been that hard. We have defined datum that were super functional. They are directly on machine featured, so they should be repeatable. They are quite easy to use, and the definition is clear. So this one was the easiest. So our next example will be a casting. So here we have a casted knuckle with the machine surfaces in blue. This is a part that is reversible, so we can use the same part. We want to be able to use the same part on the left and right side of the vehicles. Generally, when we talk about a cast part, we have two kind of requirement to define. We will have one set of requirement for the final machine part and one set of requirement for the casting. So we will talk quickly about the casting requirement at the end, but today we will mainly focus on the final part requirement. So let's start by looking at how it is installed in the vehicle. So first, we'll have the ball joint that will hold the part at its center. So this type of connection will lock all degrees of freedom in translation, but our part will remain free to rotate in any direction around that point. Then we will attach the second joint at the top of the part. So this connection will have the effect of locking the rotation in X and Y, like this. So once these two connections have been made, the only movement that the part will be able to make is rotate around the Z-axis. So that last degree of freedom will be constrained by bolting the last interface, so the steering arm of the vehicle. So what could it look like in terms of datum if we try to define exactly the way the part is located in the next assembly? Well, first we would have that ball joint that could constitute a datum target A. Then the joint at the top could constitute a second datum target that we would call B. And finally, our last connection with the steering arm would define a datum plane C on our bolting surface. But if we look at the way it's defined right now, we have some problem with the way it's defined. So first, translating the reference system in GD&T may be complex and hard to explain. So as you see, the datum are not on physical feature of the part. Also, the datum reference frame may not be easy to establish during inspection. So as you can imagine it, to be able to inspect that, you will need some kind of complex inspection setup to recreate the true datum from the physical element. Also, the datum reference frame does not take into consideration the symmetrical nature of the part. So remember, we want this part to be used, the same part to be used on both sides of the vehicle. Also, it's possible that the upper datum will be subject to additional variation during the manufacturing because it's a small hole drilled at an angle at the edge of the part. So if we look at our evaluation grid, yes, we are super functional, but repeatability might not be that good. It really won't be easy to use, and it's far from being clear. So it might even necessitate further instruction outside of the drawing to be sure that everyone understands exactly the same thing. So because of this, we will take a step back and try to see if there aren't any other functional feature that could be used on the part. So we will mainly look at all the machine surface in blue because we know that they are functional, and if we choose them as a datum, we'll have datum with a good surface quality because they are machined. So if we look at the part like this, we have the big machine diameter right there in the middle. So that could constitute our primary datum A. On the on the blue machine diameter. On our little axis system, that would log the translation and rotation in X and Z. So then we could have the machined width right here. So this is the width in which we insert the part that make the connection with the main ball joint. So that one would log the rotation around the y-axis. And at last, we could have the bolting surface of the same connecting part right here. So that would log our last translation along y. So in the end, with our new definition, we will have a datum that is defined, all the datums that are defined directly on physical elements. We will also be able to use the same definition for the two type of part, left and right. And we will have the datums that are all orthogonal and machined in the same setup. So if we bring back our evaluation grid, we might not be directly on the exact feature that locate the part in the next assembly, but we are still on functional features. So we are still good functionally wise. All the datum are machine surface, so, and also they are all created in the same setup. So we should have a good repeatability. They are all easy to use. No need for a complex setup like the first definition we had, and the definition is a lot clearer. So to come back quickly on the fact that this was a cast part, it is important to say that we might have a second set of datum to control the casting. So these datum will often be datum target and look a bit like this, what you see on the screen. So to define correctly these datums, it will be important to know how the part is manufactured. So the important point that we will look at will include the geometry of the mold. Also, we will look at how the casting is located in the machining jig, and we will also look at the process defect. So for example, if we have a parting line in our casting, we will try not to define datum directly on that geometry. So we won't go into much more detail about the manufacturing datum, but if it's a subject you would like us to cover in more details, just tell us in the survey at the end, and we'll try to come back to it in further webinar.
Yeah, and regarding this, maybe what I could add is, and we had those questions in the earlier webinar we've made, is how to make the link between the datum targets you see now on the screen and the final datums for the final component. And that's in such case where you have a casting like that, most of the time the link between the two will be a profile tolerance on certain of these features. So you might see on your drawing tolerance on a profile or surface there, and then that would bridge pretty much the datum targets on which these the datum targets on those specific surfaces, and then to the end where you have your datum on your machine parts, on machine surfaces. So that's usually the link between the two you will get. But most of the time, the datum targets will be defined by the manufacturer at the end. So he's going to have the option and the choice to choose which datum targets he'd rather have, depending on his setup for machining.
A team effort.
Yeah, it can be a team-based effort also with the OEM in different cases. But of course, it depends on how you machine and are you going to manufacture those components.
Yeah. So in summary, what we wanted to show with this example was that, so first, to correctly define datum, we sometimes have to take a step back and consider more than one solution. Also, the way the part is located in the next assembly is a good way to start, but it's not always the only option to consider. And also, for some type of part like casting, we may have a datum reference frame specific to the manufacturing of that part. So the next type of part is welded part. So the difficulty with these type of part is they will often come with a high level of deformation. Also, the rigidity of this part is sometimes ambiguous. So some assembly will seem rigid if we think about it as a small part, but they will need to be considered flexible when they are larger. So the part that we will look at for our example for that type of part will be the front subframe. So this is the part that will be used as a substructure for the installation of the steering system and the suspension. So it will this will ensure a good positioning of the system with the rest of the vehicle. So let's first start by looking at how the part is installed. So the first thing that we will do is to place the assembly on the frame like this. So this will create a plane support on the two surfaces under the frame. So this will look the translation in Z and also the rotation around the X and Y axis. Once that is done, our part is only free to translate along X and Y and also spin around the Z axis. So by bolting the bolt pattern that we have available right here, we will look all remaining degrees of freedom. So our part is now fully constrained. So what does it all look like expressed with GD&T language? Well, first we will have our mounting surface on which we will define our datum A. And then we will have our 8-hole pattern that will constitute the datum B. So at first sight, where's the problem? That seems like a good datum definition. Well, the problem is that the feature we have chosen on our part might be subject to a lot of variation. So what we will see is in terms of repeatability, we won't be that good. So what could be a solution to that? So one might suggest that we could choose a datum which locally have less variation. Like here, we could choose only one of the 2 legs of the wellman instead of both. So indeed, it is true that if we look at the surface quality individually of only 1 leg, it will be a lot better. But the problem with that is that one, it doesn't really represent the functionality of the part, but above all, it will just create projection, even more projection at the other end of the part. So that won't be the best solution. So the next step would be to go and have a look into the design and manufacturing strategy. So maybe try to find the reason why we have so much variation. So in our case, we would go see into the connection between the bend tube and the laser cut base plate. And by looking at this, we can see that the way the connection is made, all the variation of the frame are transmitted to the support plates where we have our datum. So one idea could be to try to modify the connection in a way that do not transmit the variation of the structure to the support plate during the manufacturing. So we could, in the end, we could end up with a new design, an assembly process that would look a bit like that. So what we see here is that, yes, the structure will bend and deform. We really can't avoid that with weldment, but we will be able to keep this the surface quality and stability of our datum. So this will ease a lot the control and assembly of the part. So in summary, what we learned in our welded part case study is that first, welded part will almost always have some kind of deformation. So we need to know how to consider these deformation because we often can't avoid them. Also, the design must consider the manufacturing limitation. And also we need to be careful when choosing datum and ensure that we make sure that we don't create projection that will increase even further the variation. So our last type of part is the most complex one, so a flexible plastic part. And I want to say for this one, we will really only scratch the surface. So there's so much to say about flexible part that it could be the subject of an entire webinar all on its own. But the difficulty for that type of part are first, we might have some complex geometry, but the true nature of the complexity is obviously that they will deform during the manufacturing process and during their assembly. So like in the example here, our ATV fender will bend on that flange during the installation. So this is really the main difference with other type of part. So the first step when defining datum will be the same as with any other type of part. So we will look at how the part is installed in the assembly and mostly in which sequence. So this is especially important in the case of flexible part because a different installation sequence might have a larger impact on the final geometry of the part itself. So in the case that we have here, we will support the part against the structure right here on the main bolting interface. Then we will bolt the hole at the back of the fender. So once that is done, the part can only rotate around that point. So if we bolt the slot at the front, the part won't be able to move anymore. So at that point, for any other type of part, we would be done because we have locked all degrees of freedom. So the part is fully constrained. But in the case of this part, we must specify one last step, which is the bolting and clamping of the inner fender liner. So the part will deform under that new constraint, meaning that the geometry of the part will change. So because of that, it is important to consider this in our assembly sequence. So using GD&T and datum, so how would that look like? Well, we would first have our datum plane A. Then the hole at the back has our datum B, and the width of the slot would constitute our datum C. So what are we missing? In our assembly sequence, we had these 4 holes. So they were bolted at the end. So what do we do with those? We can't really define them as datum since we are already fully constrained with datum A, B, and C. So this is where it will be a bit different with flexible part. And what will be different is we will have to specify the constraint state of the part. So for an example like this one, we would do this in a drawing note and ask that the part should be controlled while the datum A is constrained on a flat surface, and that our pattern of hole be bolted using M6 bolts with a torque of 9 to 15 Newton meter. So this is about it for flexible part. I know it's short, but we have only 1 hour, so we are already arriving at the conclusion part of the webinar. So just to conclude, what we have seen in this webinar and what you need to remember is that first, defining functional datum is really the basis of a good geometrical description of a part. Also, to do that correctly, we must know how to balance, amongst other, the functionality, the repeatability, the ease of use, and the clarity. And also remember that this is the starting point for the discussion with your supplier. So it's really worth it to take the time and select them and define them correctly. So Martin.
Yep. Yeah, and then like we do at each webinar, actually, and Cedric has covered quickly actually different topics. So he went through different type of parts, and so if you have a more specific question to your application and that require maybe a bit more time and reflection to think about, we're there to support you. Don't hesitate to come back to us and ask questions. There are different ways we can work with you guys. So here we're presenting a kind of like a webinar, which is close to what training would be. So we can offer training, but we can also offer coaching for your different resources. And you can also ask for a service on a la carte basis. So if you need support for, I don't know, 40 hours for a specific topic, we offer the services of our expert in this way. So we can support your product development, and then you are also, if you are in going production, so if you have issues for products that are in services, on the market, and you're seeing I don't know, premature wearing on certain component, it might be related to a dimensional management issue. We can support you, do a root cause analysis, and work with you. So some of our customers will buy a bank of hours for the whole year, so they'll buy 500 hours and they just call up when they have a specific issue, so we can support their internal team, engineering team. So keep that in mind. We are here to support you. So it's not only giving training, it's also being able to support your product development methods. So and that pretty much covers, and we have a whole bunch of tools. I see the slide here with 3DCS and PolyWorks. So we have a whole bunch of technologies and software in-house that we can use to do variation analysis and dimensional inspection, reports, and all that. So sometimes you might not have all those tools in-house. So that's where it's important to come back to see us and see how we can support you with more advanced tools for more advanced problem. When we're talking about flexible components, I mean, this is definitely more technically challenging for the team sometimes to correct different issues they would have with such large flexible components. It could be body panels or inner liners for a vehicle, and that might require a more advanced tool that can make variation analysis in the 3 dimension, not only in like what we've showed today is pretty much like a variation that would be like in 1D or 2D, but when you get into 3-dimensional issues assembly, it gets more complicated for the normal human being to interpret all the variation possibilities. So
also, obviously, this was a broad overview of how to define datum, but if you want to have more details about some specific case, don't hesitate to say it in the poll at the end. And
yep, absolutely, that's a good point, where we use your comments and your question in the survey to develop content that is more specific for the next webinar. So it's really important you guys share that. We have a long question actually that we received. Well, it's going to take a few seconds.
I think it's more like a comment than a question.
Comment? Yeah. Okay. Have you read it? because it's I'm just starting to read it. So
yeah, I'm reading it. But yeah, it's a comment about some things.
okay, yeah, it's more common. Okay, and that's appreciated. We'll take that and definitely either take it and improve our presentation, or make sure we have showed correctly sometimes how we interpret and how we put the things in the presentation. Also, I have yeah, for flexible part, I have a question where if I have a flexible part with the rigid area but that are not functional, is it recommended to put the datums on these area? And that would be a question for Cedric, you might be able to answer. So if you have a flexible part with some more stiffer areas that are not functional, so ribs maybe in a body panel or something, is it recommended to put datums on certain?
The case in our part. If we look at how the part is made, there's really one area that is more flexible than the rest. So what we did here is we define the datum, the true datums on area where they were more rigid, and so here and the connection at the back. But what we did in addition to that was to specify the constraint condition of all the area that were less rigid. So this is how almost all flexible part will have some area that are more rigid and some other area that are more flexible. So the idea is to simulate as best as we can the way the part will be installed in the next assembly.
Yeah, and we at Creaform, we do inspect. We do a lot of services for inspection, and people sending us samples, like 30 part samples for first article inspection or PPAP process, and then it's always the same thing. So you make a setup where you can put your datums up to 0, and then you're gonna have to over constrain your component, which is flexible, and then like Cedric was in this specific case where he's showing the 4 holes that needs to be bolted actually. So you put all these holes and make sure that you're equivalent as if you would be assembled on the vehicle, and then you can inspect your parts. So it's really important to reproduce the natural, I would say, assembly of the part, so that you can. So that's where selecting datums is, and how you choose them is really important. That you can, in flexible components, you have to over constrain them to hyperstatic state, I would say. So here another one would be. How do I define the tolerance on my datums? We saw through the whole presentation, Cedric, that you put tolerance on your datums. So how would you do that? What are the factors that are influencing the tolerance you put on your datums?
The first example of that was here when we define, for example, the perpendicularity on our datum B to A. So that's a good example. Well, this is a hard one. It will depend really on how the part is installed and what is the need. So if we look at this one, for example, the way it's installed in the assembly is like this. So the perpendicularity that we will have, the defect of perpendicularity that we will have between the shoulder and the diameter will actually create kind of a gap between the spindle and the knuckle. So the way we would define this one here is by choosing what is the maximum amount of gap we are able to allow between the shoulder of the boat and the knuckle. So this is for this one. Another case where we had the requirement tolerance on our datum was this one, for example. So this is a bolted interface. So we have a flatness on that interface. So the value that we will put there will be the value that we are able to accept, the gap value that we'll be able to accept between the part and the next assembly. So between the gray and the yellow part in that example. So as you can imagine, 1.5 millimeter of flatness plus the flatness of the yellow part as well. So this will be the maximum gap that we will allow between the two parts.
We just have another question here. Is it common to use the CLIC method to define the functional GPS, and how you can estimate the IT value? And how can you estimate the IT value?
Not familiar with the CLIC method.
Yeah, that's it. Me neither. So maybe if you, the person asking the question, could elaborate on the click or CLIC method. I'm not familiar with that.
Yeah.
Method for geometrical specification of product. Okay. Okay. Well, I don't know. Have you ever heard about that, Cedric?
No, never heard about that.
Yeah, so sorry. And maybe we'll take this question on after the meeting. We can send an answer to, yeah. So I see that the person has sent some information about the CLIC method. So we'll
That's
take a look at that. And
yeah,
it's really definitely interesting. So we'll take a look at that and maybe answer more specifically to you on that. I think that's pretty much it in terms of questions. So if I don't know if anybody has a question, it's time to do so. We pretty much don't have anything else. So I'll take maybe 30 seconds. If anybody has some other question or comments, it's time to do so. Other than that, when we're gonna close the, when Cedric's gonna shut the webinar, you're gonna have a survey. So I think we're repeating a lot here, but make sure you answer those. I mean, I think it's like 5 questions. So, but your comments are very welcome. We adapt our presentation to the comments. So so there's gonna be another webinar coming up in a couple of weeks, most probably. So, and the content will be adapted to the comments that people have made. So, so it's appreciated if you can take some time for that. And here are our contact info also on the last slide. So there's the website, a lot of information on our website or links to either content or videos on our YouTube channel. And then Cedric and my email also is there. And on LinkedIn, on our LinkedIn page, official Creaform Engineering page, there's also some links and content that we share there. So if you guys are more interested in finding more there, I mean, we've put some of our latest webinar also in there. So if you've missed the first one, you can always catch back and find those. And it's going to be the same in the future. Also, you'll be able to see future content we'll put in there. So that wraps it for today. So 45 minutes, which is good. I mean, we fell right into the time we thought we would be, and we hope that you enjoy that and it was instructive for you. And we're looking forward to making some more webinar in the future. So hope you guys would be part of that also. And hope you all guys are safe and sound and take care. And hope to see you later on. Thank you.
Thank you very much, everyone.